Hello, we are Team Mega Men, and our project is Bill and Omar's Excellent Adventure. Essentially, we are making an arcade-style game, which is a single-player game. It can be played in the arcade cabinet using the JAMA interface, and it's a challenging game for anyone who wants that kind of experience. So in terms of game functionality, the character can move left, right, up, and down, as well as attack the enemy. The enemy AI will patrol certain areas and will attack the player if the player is in that specified region. And we have boss battles that feature unique AI. To paint the game, we have created custom sprite sheets, which are designed as a large image which feature many different frames of an animation, and then these animations are referenced with our Verilog code to create fluid and smooth transitions between each action. As you can see here, our title screen, as well as the level design of each level, has also been created using sprites. Although these do not feature animations due to the size limitations, our game over screen does feature an animation which you will be able to see later. Just as a brief specification overview again, it's basically a side-scroller game. You can play as two different characters, either Bill or Omar, and we have custom artwork that uses the sprites which we have created to paint the game, and we use the Nexys3 Spartan 6 FPGA board. Our system interfaces with the JAMA interface so that you can play it in an arcade cabinet, and we load the sprites onto the board using the Adept tool. In terms of player movement, the player can move left, right, up, and down, as well as attack. The clock divider samples button presses, and the bounds of the screen are defined by us for each level. In terms of the specific Verilog behind this, we check if the player has been jumping. If the player is jumping and is in range of the platform, then the different static variables will be redefined so that the new ground is the platform level. Otherwise, if the player is falling or standing on a surface other than the platform, the normal ground level will be used as your base. In terms of the combat system, the input of the attack button is checked to see that it isn't being held down, and if it is being held down, it doesn't constantly register that an attack is occurring. If the character faces right or left, the animation for the attack will correspond to the side that the character is facing, and in terms of the specific Verilog, you basically check each time if you are in the range of the enemy, whether it's a generic enemy or a boss enemy. If you successfully land an attack on an enemy, then you'll kill the enemy and trigger the next level to begin. However, if you are attacked by the enemy, you yourself will be killed and you'll be sent to the game over screen. In terms of enemy AI, we have enemies defined to patrol certain areas of the level, and if they find you in the same X and Y coordinates, then they will try to attack you. You can dodge these by jumping over the enemy, but if you get hit and you're on the same plane as the enemy, as in the ground or the same platform, then the enemy will be able to kill you. In one hit, you will die, and you will have to restart the game. In terms of the RAM controller, it reads in data based on the address calculated by the sprite controller. By reading in 2 bytes at a time, you can see all of the information about the RGB values correctly. This also gives us the ability to use larger backgrounds and larger sprite sheets to see the full implementation of our animations and our design. Essentially, the way it works is the sprite controller will read into the DRAM of the FPGA and display the different backgrounds, enemy placements, and legal coordinates based on the level counter. We use static parameters to find the different sprites located on the DRAM, and by adding this corresponding parameter to the address calculation, you'll be able to see the proper level loading. Here you can see our block diagram, which receives movement information from the joystick of the JAMA interface, as well as the attack button. These are processed by different controllers, essentially, which will change the X and Y coordinates, as well as the memory offset. These get sent to the VGA sprite controller, which references the DRAM of the FPGA, which sends the RGB values back to the sprite controller to display the VGA output. In terms of design trade-offs, we had a lot of issues with the memory limitation of the FPGA board. Originally, we wanted to use the block memory generator that is, it works within Xilinx, but we found that using the Adept tool, we were able to get some of our more intricate animations back, and we were able to actually load backgrounds. And obviously, there's the time constraint for content. We would love to implement a lot of these higher level features like more levels, more enemy types, and more bosses, but due to the time constraints of the course, we were unable to feature any more than what we have delivered. In terms of the work split, Omar did the sprite design, memory loading, animations, and menu system, while Bill focused on the movement system, combat system, and platforming system.
Here we can see if the enemy hits the player, it goes to the game over screen. The player's movements on screen are controlled by the 5 buttons on the FPGA, left and right for the horizontal movement, up for jump, down for jumping down off of a platform, and the middle button for attack. Once the sprite and the binary is loaded onto the board using the Adept software tool, the main menu is loaded. When the player hits the attack button on the FPGA, it goes to the first level, where the player encounters the enemy. After the player strikes the enemy, it goes to the second level. When the player strikes that enemy, it goes to the third, at which point the game ends.